What if the batteries of the future didn't need hours to charge but could absorb energy faster than you can blink? Scientists just published results showing quantum batteries that hold their charge 1,000 times longer than before. But before you get too excited, we're talking about microseconds, not hours. Yet this breakthrough reveals something profound about how nature stores energy at the quantum level. For over a decade, physicists have chased an almost magical idea. When atoms or molecules work together quantum mechanically, they can absorb light collectively, charging faster as you add more units. Think of it like this. One person filling a swimming pool with a bucket takes forever. Add more people and it fills proportionally faster. But quantum batteries? Add more quantum units and suddenly they're filling the pool exponentially faster, breaking the rules we thought governed energy transfer. The first real quantum battery built in 2022 confirmed this superabsorption effect. Researchers filled a tiny cavity with dye molecules between mirrors, creating a system where all the molecules could absorb light together as one unified quantum state. The charging speed was incredible, exactly as theory predicted. There was just one problem. The energy vanished almost instantly, leaking away in nanoseconds. The same quantum effect that made charging super fast also made discharging super fast. Like trying to fill that swimming pool with a massive hose while someone simultaneously opens all the drain valves. Now researchers from RMIT University and CSIRO in Australia have found a way around this fundamental limitation. Their device still uses superabsorption to charge rapidly, but then does something clever. It transfers the energy to a different type of molecular state that can't easily emit light. These are called triplet states, and they're nature's way of creating temporary energy storage. Here's what makes triplet states special. When a molecule absorbs light normally, an electron jumps to a higher energy level, but keeps its quantum spin opposite to its partner. That's a singlet state, but sometimes the electron flips its spin during the jump, creating a triplet state where both spins point the same direction. Because of quantum mechanical rules about spin conservation, the molecule can't easily emit light from this state. It's trapped, holding on to that energy much longer. The Australian team built 5 different devices, each containing 2 layers. The first layer has rhodamine dye molecules that superabsorb incoming laser light. The second layer contains palladium porphyrin molecules with accessible triplet states. When light hits the device, energy flows from the superabsorbing layer to the storage layer, where it gets stuck in these triplet states. The best device held energy for 40 microseconds. That might sound pathetically short, but it's 40,000 times longer than the previous record. Think about what's happening here at the molecular level. Millions of molecules are working together, sharing quantum states, absorbing photons collectively. Then that energy cascades into dark states that can't radiate it away. It's like a crowd of people catching rain in buckets, then quickly pouring it into underground cisterns where it can't evaporate. The rain collection happens at quantum speeds, but the storage bypasses the quantum effects that would normally cause immediate loss. Lead researcher Daniel Tibbin admits they're still only inching toward a practical quantum battery. 40 microseconds won't power your phone or car, but crossing from nanoseconds to microseconds proves the fundamental physics works. The superradiant decay that plagued earlier devices can be suppressed without sacrificing the superabsorption advantage. This matters because conventional batteries face hard physical limits. Chemical reactions can only proceed so fast. Lithium ions can only shuttle between electrodes at certain speeds. Heat builds up. Materials degrade. Quantum batteries sidestep these constraints entirely. They don't rely on moving atoms or breaking chemical bonds. They use the collective behavior of quantum systems to capture and potentially release energy at speeds chemistry can't match. The implications stretch beyond batteries. Solar cells lose enormous amounts of energy because absorbed photons create excitations that recombine before they can be harvested. Adding a quantum battery layer that rapidly captures light and holds it in dark states could dramatically boost efficiency. Photodetectors and quantum sensors could benefit from the same ultra-fast absorption and temporary storage. But let's be realistic about the challenges. Extracting useful electricity from these devices remains unsolved. The current prototypes store energy but can't deliver it on demand. Scaling from microscopic cavities to practical sizes while maintaining quantum coherence seems nearly impossible with current technology. The materials involved, exotic dyes and porphyrins, aren't exactly environmentally friendly or stable over time. There's also a deeper challenge. Quantum effects are fragile. The slightest disturbance from heat, vibration, or stray electromagnetic fields destroys the delicate quantum states needed for superabsorption. Creating devices robust enough for real-world use while preserving their quantum properties is like trying to keep a soap bubble intact in a hurricane. Some researchers are exploring even stranger approaches. Theoretical work suggests that quantum batteries operating with indefinite causal order, where the sequence of charging events isn't fixed, could extract more energy from weaker sources. Others propose using spin waves in magnetic materials or coupling batteries to environments with quantum memory effects. Nature might already use similar tricks. Some photosynthetic complexes show signs of collective quantum absorption, though whether organisms truly exploit superabsorption remains controversial. The 2025 breakthrough doesn't revolutionize energy storage overnight. We're not getting quantum-powered cars or grid-scale quantum batteries anytime soon. What it does is crack open a door that physics said should exist, but engineering couldn't reach. By showing that superabsorbed energy can be transferred to protected states, the Australian team validated decades of theory and created a platform for the next generation of experiments. Consider the strange reality we're approaching. Batteries that charge faster when you make them bigger, energy storage that exploits quantum entanglement, devices where the boundary between light and matter blurs into hybrid states that don't exist in our everyday experience. Each breakthrough inches us closer to technologies that would seem like magic to anyone living today. The universe stores information and energy in ways we're only beginning to understand. From the quantum states of molecules to the spin configurations of materials, nature has evolved countless mechanisms for capturing and preserving energy against the relentless pull of entropy. This latest quantum battery might store energy for mere microseconds, but it represents our species learning to speak nature's quantum language. And once we're fluent, the only limit is our imagination.